Good evening, everyone. I welcome you all to the last problem solving session for the course Computational Fluid Dynamics. And the course instructor is Professor Sreenivas Jayanti from IIT Madras. So, we'll just start the session. So, yeah, we have seen 11 problem solving sessions for this course, and we have covered almost entirely from the basics like flow through a rectangular domain or flow through a triangular domain, where we used finite volume method and also the finite difference method also we saw initially, and then slowly we moved on to discretization techniques and like with finite difference approach how it is solved. And then further we have just seen how to solve Navier-Stokes equations for the like compressible as well as the incompressible system. And then with that, we also saw like what are all the types of equations, like how it is classified, like the how partial differential equations are classified as elliptic, parabolic, and hyperbolic. And also we saw few like various techniques to solve them. And also we saw how to discretize those equations with various discretizing schemes with different orders, like central difference, forward difference, and backward difference. And also we saw the types of boundary conditions like Dirichlet, Newman, and so on. Like, and also like we saw stability analysis, um, and then how to reduce the oscillations, like how to make it stable, like conditionally stable systems and unconditionally stable systems, and so on. We have seen so many things throughout the course, where we have solved a few problems associated with it, and the theory behind it was taken by the professor. So, and in the last few classes, we have also seen the numerical methods associated with solving these problems. Um, how what are all the various numerical methods that can be put in CFD to solve them easily with easy convergence of the solutions. And then we have also seen the convergence criteria, and then we have seen few techniques like multi-grid approach, successive over relaxation, alternating direction implicit, and everything. And in the last class we also saw about the meshing techniques, like structured grids and unstructured grids, and what are all the advantages of them. And like also we saw how to go forward with the unstructured meshing, like advancing front method, Delany triangulation method, everything. We have discussed the problems behind these techniques. And this class, this week, the course deals with the turbulence. So the problems from this week mainly focuses on turbulence, like time and length scale of turbulence and time averaging, like how it deals with that, and or what are all the basic concepts we should know when we are dealing with the turbulence in a problem. In CFD, when we are dealing with if we consider about the real life problems, there are various systems that deal with turbulence, like, so it is important to understand the concept behind the turbulence. Concept behind the turbulence, so that it would be easier for us when we are dealing with them, and when we are doing CFD problems, it would be helpful for us. So we'll move on to this today's session. Before that, if any of you have any doubt related to today's sessions or previous sessions, please feel free to ask. So your feedbacks are always welcome. You can say uh, at the end of the session, or anything is fine. Uh, yeah, we'll just start today's session now. Which of these, as many of you would have known by now, the first few problems are from the week 12 non-graded assignment problems, followed by the assignment problems from the week 12. Also, you would have probably solved all these problems. If, the session is just to help you in this, because in addition to this, you must also be knowing that this week, NPTEL exams are around this weekend. So it might also be adding us a quick revision. So yeah, we'll just start without any further things. So these are all the non-graded assignment problems. So which of these is a characteristic feature of turbulent flows? Chaotic fluid motion, high diffusivity, high frequency fluctuations. So options are either only chaotic fluid motion, or chaotic fluid motion and high diffusivity, or chaotic fluid motion and high frequency fluctuations, or all the three involving chaotic fluid motion, high diffusivity, high frequency fluctuations. Although the answer is given over here, just take a moment to think of why, like, the answer to this problem is chaotic fluid motion, high diffusivity, high frequency fluctuations. So although it is known, please take a moment to consider why it is so, and then we'll discuss the answer. So, like, we all know that we can classify the flow as turbulent or laminar flows depending on how the fluid flows. So, consider it is flowing through a pipe. So, if it is going in a straight line, we call it laminar flow. There is no much mixing or anything taking place in the system. As opposite to this system, where the fluid is going like this and there is continuous mixing like this. So this is known as turbulent flows. So what exactly happening is that in turbulent flow, The fluid undergoes so much fluctuations. It is not a character. I mean, we cannot characterize it to be a regular thing. Like fluctuations happen randomly. Whereas in laminar flows, the flow happens smoothly. Whatever the parameters that are getting transferred, it gets transferred layer by layer, as opposed to in turbulent flows where it is frequently fluctuating and irregular mixing happens. So the fluid, I mean, it keeps on changing at with the fluid motion, or the fluid velocity keeps on changing with respect to time, as well as it's, I mean, both of its magnitude as well as the direction keeps changing. Therefore it is highly turbulent. We associate it as highly turbulent. So we can see that it is chaotic fluid motion is there, high diffusivity is also there, like it gets mixed randomly, and high frequency fluctuations is also there. So obviously the answer to this is 1, 2 and 3. So answer is option D. I hope this is clear. Now we'll just move on to question 2. The time interval for time averaging of flow governing equations should be such that it is as large as possible. It should be much larger than the time period of the largest eddy. It should be much larger than the time period of the smallest eddy. It should be much smaller than the time period of the smallest eddy. So the answer to this problem is given as option B. So can anyone answer why it should be much larger than the time period of the largest eddy? So basically what happens in time averaging is that it provides the net effect from the turbulent, like when it is disturbed. So it provides the time, like net effect in the time interval. So like when we are dealing with the turbulent flow, the Navier-Stokes equation and the conservation of mass, like those equations, we require it to be done in a very smaller grids, because we need only then we can go for capturing the eddies. uh, if the grid sizes are very smaller, we know that it would be taking a very large simulation time. Thereby, it is making it computationally expensive. So we should be going for the time averaging thing. In By doing so, we will obtain the governing equations in terms of the time average parameters. So when the eddies are getting formed, if the time period of for the larger eddy, consider a smaller eddy and larger eddy. If we take the time interval to be greater than the time period of the largest eddy formation. So in that case, it would make sense for us to completely capture that fluctuation, thereby making use of the time average parameters in the equations. So in those cases, we would be going for the time averaging for flow governing equations with the time interval to be larger than the time period of the largest eddy formation. I mean, time period should be larger than the time period of the largest eddy formation. So that is the case. So we it should be like, if we take the largest eddy and smallest eddy and largest eddy. So if we capture this movement, this phenomena completely in the smaller in the time interval, thereby the fluctuation is completely captured and put it in the time average flow equations. If we, on the other hand, if we go for this smallest eddy, it is the phenomena is not completely captured in the time averaging equations. Therefore, we should go for it should be much larger than the time period of the largest eddy. So now we'll just move on to question 3. Mixing length varies with fluid viscosity, Reynolds number, normal distance from wall. So options given are either only fluid viscosity, or either only Reynolds number, or only normal distance from the wall, or it is both Reynolds number and the normal distance from the wall. So can anyone say what is Prandtl mixing length? Or else, if it is, if you are not willing to say, just think and recollect in your mind. So basically what it denotes is that the mixing length is such that it is the diameter or the length of the small mass of a fluid moving as a whole in each individual case. Or else, like, we can say that it is the distance traveled by a mass of this type before it gets blended with the surroundings. Therefore it is the okay, here it is raining very well, so please just be connected. If there is any power fluctuations, it would take some time to get back or connect back, so till the time please wait. Okay. So what is it meaning is that it is the mixing length is the smallest, length of the smallest, eddy. It maintains as a small portion before it gets blended with the surroundings. Consider a fluid particle like this moving in the fluid flow domain. So this is the distance it travels, that is the mixing length. It is the mixing length. The mixing length is such that in the fluid particle travels as itself before it gets blended with the surroundings. Sorry, I didn't discuss the answer. So what it basically denotes is that fluid viscosity does not come into picture. Also, Reynolds number does not come into picture. Only thing that comes into picture is the normal distance from wall. The distance from the wall basically considers or basically affects the how much distance the particle moves before it gets blended with the surroundings. Therefore, only normal distance from wall comes into picture. So the answer to this is option C. or option 3. So now we'll just move on to question 4. So in question 4 it is given that we are solving the case of a steady developing turbulent flow between two infinitely wide parallel plates using K epsilon turbulence model. For this case, the number of differential equations we need to solve is. So basically it is given we are solving a turbulent flow between two infinitely wide parallel plates using K epsilon turbulence model. So the number of differential equations that we need to solve is given by. So the first one is, if it is a fluid flow between two parallel plates, so how many equations do we have? We have one mass equations or the continuity equations and momentum conservation equation, or the momentum conservation equations, or I mean not or, it is the Navier-Stokes equations. So it is 1, and we have x and y momentum conservation equations, so basically 2. So from this itself we have 3 equations. And since we are using K epsilon turbulence model, we have additional 2 equations, that is K for one equation for K and the epsilon, that is the kinetic energy equation and the kinetic energy dissipation rate equation. So the number of equations that we need to solve is given by 5 equations, that is one one mass conservation equations, 2 momentum conservation equations, 1 kinetic energy equations and the kinetic energy dissipation rate equation. So 1 for K, 1 for epsilon. Therefore it is totally making 5. Let us see what are all the options given. The first one given is 5. That is right. And other options given are 4, 3, 2. I mean all are wrong. So basically the answer is option 5. I mean answer to this is option A, that is 5. We'll just okay. So in this week, the number of problems given in non-graded assignments are only 4. So with this we'll wrap up the non-graded assignment problems and we'll just start with the assignment problems for the week 12. So the first, a figure is given. Figure 12.1, unsteady turbulent developing flow of water, rho is equal to 1000 kg per meter cube and mu is equal to 0.001 through a rectangular duct of dimensions L, W, H such that L is very much greater than H and W is equal to 1.5 times of H. The inlet velocity is uniform across the inlet plane but varies with the time. Okay, so here it is given that inlet velocity is varying with time, outlet is 0 gauge pressure. So in the question 1 it is, I hope things are clear from this statement. In this statement what are all the things that are given is that this is the figure 12.1 is the figure for this problem. So basically water is flowing through this rectangular duct. In this rectangular duct, length is very much larger than the width, larger than the height, and similarly width is 1.5 times of height. And also but varies with time. Yeah, velocity is not a constant, is uniform across the inlet plane. Velocity across the plane is constant but it is varying with time. So basically outlet is 0 gauge pressure. Where is my cursor? So now it is that we'll just move on to the problems for this week. So again I repeat, if there is any issues during the session, please wait a moment, do not leave the session. There may be some power interruption because of rain. So yeah, we'll just move on to question 1. In question 1 it is given that if h is equal to 2 centimeter, then the value of V in for the flow to have a minimum Reynolds number of 550,000 is. Okay, options are 1 meter per second, 2.1 meter per second, greater than 2.5 meter per second, or less than 0.25 meter per second. So what is Reynolds? Reynolds number is given by so we know here it is a rectangular duct, so D we cannot take it normally, therefore it is a equivalent diameter. So how do we calculate is that flow cross section area 4 into cross section area divided by wetted perimeter. So if we are considering the rectangular duct, and the cross sectional area would be 4 into width into height divided by width, height plus width. So in this question it is given that width is equal to 1.5 times of h. Therefore D is equal to 4 times of width into h, that is 1.5 h square divided by 1.5 h plus h is, that is 2.5. So basically it is 4 into 6 by 2.5 h. So it is 60 by 25, 12 by 5, or 2.4 h. Here h is given as 2.2 centimeter. So it is 2.4 into 2, that is 4.8. 4.8. Now we substitute it back to get the velocity. So at this it is V is equal to, sorry, it is small v, Reynolds number which is given as 50,000 into mu, that is 0.001, divided by 1000, that is rho, into D, that is 4 point, sorry, 8. So the answer would be okay. Give me a moment, I'll just calculate. Sorry, actually here it should be 2 times of wetted perimeter. So again it would be 2. In that case, D would be divided by, therefore it is 1.2 H, 1.2. Finally, this is 2.4. So in that case, something is going wrong actually. 50,000 into 0.001 divided by 2.4. Okay, again here it is in centimeter, so we should convert it into meters. So 110 power minus 2 would come. If we do that, it would be divided by 10. Okay, answer is 2.083. So it is approximately equal to 2.1 meter per second. So the answer to this is option B. Yeah, it is 1 meter per second, it is 2.1 meter per second, greater than 2.5 or 0.025. Well, the answer to this is 2.1 meter per second. Correct answer is option B. We'll just move on to next question. We wish to simulate the flow through the duct shown in figure 12.1 using the K epsilon turbulence model. Which of the following statements are correct about the Reynolds average Navier-Stokes equation? We need to solve unsteady form of that is Reynolds averaged Navier-Stokes equation. We need to solve, where is my cursor? Unsteady Rand's equation because the flow is turbulent. We can use steady form of Rand's equation because the equations are time averaged. So the options given are 1, 2, 3 or 1 and 2. Well, we used to simulate the flow through the duct, that is the rectangular duct which we saw using the K epsilon turbulence model. So which of the following statements are true about the Reynolds averaged Navier-Stokes equation? The Reynolds averaged equations are basically the time averaged equations for motion of the fluid flow. So here what we do is we do Reynolds decomposition where an instantaneous quantity is decomposed into time averaged ones and fluctuating ones. So basically it gives the I mean, if there is turbulence, what happens is there are so many fluctuations. So to deal with that, we are decomposing it into two quantities. One is the time averaged one plus the fluctuations, which gives the instantaneous value profiles. uh, so we basically we can see that it is unsteady form of the equations, not the steady state form. uh, Basically, so we need to solve unsteady form of Franz equations because the flow is turbulent. I mean, we are using K epsilon turbulence model, so obviously the flow is turbulent because also the velocity is varying with time as given in the problem statement. Therefore, we need to solve for the unsteady form of the Franz equation, and also we need to solve unsteady Franz equation because the flow is turbulent. So answer to this question is option 1 and option 2. That is option D is the right answer. Okay, let us move on to question 3. I am just in a quite hurrying because I want to complete the session as soon as possible because of the weather conditions. Let us hope so. Yeah. So we wish to simulate the flow through the depth shown in figure 12.1 using K epsilon turbulence model. How many partial differential equations do we need to solve? So basically we saw the figure 12.1, that is this figure. So this is a three-dimensional figure and we need to solve for the x, y and z directions. So we have three momentum conservation equations, one mass conservation equation, so the continuity equation, and since we are using K epsilon turbulence model, we have 1 plus 3 plus 2. So why can't we just put it over here then? So number of equations is equal to 1 plus 3 turbulence. Therefore, it is giving 6 equations. So answer to this problem is option C, that is 6. Actually, we have seen a similar problem right in the previous case also. We just put the answer over there so that it would be easier for following up in the future. Rather, here it is 2 and here it is 5. Now we'll just move on to question 4. Which of the following statements is true about the turbulent kinetic energy variation within the duct for the problem shown in figure 12.1? So at a given location not close to any boundaries, turbulent kinetic energy will increase with time. At a given axial location, and at a given instant of time, turbulent kinetic energy will be higher closer to the center than close to the wall. Okay, so options given are either 1 or either only 2 or either 1 and 2. I mean both 1 and 2 or both of the statements are wrong. So what it means is that turbulent kinetic energy variation within the duct. I mean it is asking how it would vary. So basically turbulent kinetic energy is the like it is a kinetic energy associated with the smallest, I mean eddies. So we just average it out, or we calculate it using root mean square. So for a given problem, when it is not closer to any boundaries, the turbulent kinetic energy will be increasing. But we cannot associate it with how it would vary from along the center than near the walls, because the wall disturbance would be there, and it would affect accordingly. So the answer to this problem is only the A, that is option 1 is the only right answer. We'll move on to question 5. Which of the following is likely to be turbulent? Flow in a circular pipe at Reynolds number of 50,000. Flow over a sphere at a Reynolds number of 50,000. Flow over a flat plate at a Reynolds number of 50,000. So we all know like Reynolds number is used to characterize the turbulent flow. So different geometries have different Reynolds number, like Reynolds number criteria to understand the turbulence. So for example, we are very familiar with the like turbulence in a circular pipe, where we associate the values like 50,000. I mean if it is more than 2000, we would characterize it as turbulence, right? So basically critical Reynolds number for flow through a pipe is, that is circular pipe, is 2000, whereas if it is flow over sphere as given in the second option, the critical Reynolds number is around 2 lakh. So if it is 50,000, it is probably a laminar flow. And for flow over a flat plate, where we calculate it based on free stream velocity, the Reynolds number, that is the critical Reynolds number, is around 5 lakhs, not 50,000. So obviously the critical Reynolds number for the flow through sphere and flow over a flat plate is around 2 lakhs and 5 lakhs respectively. Therefore the only correct option in this given problem is 50,000, sorry, flow in a circular pipe at a Reynolds number of 50,000. The Reynolds number is given as constant for these things. So the only correct answer to this problem is a flow in a circular pipe at a Reynolds number of 50,000. Only option 1 is the right, whereas in all the other options option 1 is present, but along with that various other options like 2, 3 are also present, so which are wrong. The only correct answer is option A, that is flow in a circular pipe at a Reynolds number of 50,000. We'll just move on to question 6 now. So, which of the following are characteristic features of turbulent flows? Always three-dimensional and always fluctuating. High diffusivity, do not obey Navier-Stokes equations. So, we already saw what is turbulent flows. Turbulent flows is that such that like it is has high fluctuations, and every property like it would be varying randomly and irregularly. We could not formulate anything from that. So yeah, those are characterized as turbulent flows. From the given options, it is seen that turbulent flows are three-dimensional and are always fluctuating. It is true, right? Because all the properties keeps varying without any pattern. So option 1 is right. In option 2, it is given high diffusivity, which is again right. And option 3, it is given do not obey Navier-Stokes equations, which is false. So 1 and 2 statements are only right. So it is given in 1, which is right. Option B, it is 1 and 2. Again, it is right. Option C, it is 1 and 3. Third statement is a wrong one. Option D, it is 1, 2 and 3. Again, third statement is a wrong statement. So obviously answer to this is option B, the 1 and 2. I mean, we solved the similar problem in non-graded assignment 1, where we saw which is of the following is the characteristic features of turbulent flows: chaotic fluid motion, high diffusivity, high frequency fluctuations. Answer is option 3, option D, that is all three statements are wrong. Chaotic fluid motion, high diffusivity, high frequency fluctuations, which is what which is what we saw again here. Okay, this one, sixth one. If you are feeling any clarification is further needed in any of these problems, please feel free to stop me at any point. Now we will just move on to question 7. Which of the following statements is true about turbulence closure problem? It arises only when we time average governing equations. It arises only when we do direct numerical solutions of turbulence flows. It arises because there are too many equations. It arises because there are too many equations and too few variables. What we do with turbulence closure problem is that when we are dealing with the time averaging governing equations, the time averaged quantities exceeds the number of equations. So basically we need to know few things to go with the smoother solving of the problems. In those cases we go for the turbulence closure problems. Thereby we can solve the problems that are associating with the too many equations and too few variables. Therefore, we go for the turbulence closure problems. So, it arises only when we are time averaging the governing equations. This is the true statement. It arises only when we do direct numerical simulations of turbulence. This is false. And it arises because there are too many equations and too few variables. This is a too generalized statement. So, again, this is false. So, answer to this question is only option 1. Option A it is 1, option B it is 2, option C it is 1 and 3, option D it is 2 and 3. So answer to this problem is option A, which is 1. So we'll just solve question 8. Just a minute, I'll just take okay, I'll just solve this and then take a break. Which of the following statements is true about Reynolds stresses? They are not stresses per se, but stress-like quantities. There are only 6 independent components in Reynolds stress tensor. They are constant across the cross-section of a pipe in a fully developed flow. So options given are either only first statement is right, or 1 and 2 statements are right, 1 and 3 statements are right. Option D, it is 1, 2 and 3 statements are right. So just take a moment to, answer is obviously given, it is 1 and 2 statements are right. So just take a moment to understand why 1 and 2 statements are right. And we will discuss the answer shortly. So basically, the what is Reynolds stresses? When we average the Navier-Stokes equation, it is a component that we get from the averaged ones, where we use this. So basically, they directly do not mean these stresses, but they are like stress-like quantities. Basically, they arise from the we have a advection quantity in the Navier-Stokes equation, right? So that from that nonlinear term, when it is decomposed and averaged, like when the Navier-Stokes equations are decomposed into an average when we are dealing with the turbulence quantities, what we do is that we replace the instantaneous ones with the time averaged ones plus the fluctuating quantities, right? So in that case, when the advection term comes into picture, Reynolds stress comes. So they are not stresses, but they are like stress-like quantities. So there are only 6 independent components in Reynolds stress tensor. and they are not actually constant across the cross section of a pipe in a fully developed flow. Therefore, only 1 and 2 statements are right, which is given by option B. Now we'll just move on to question 9. Which of the following statements is true about eddy viscosity? First one, it is a flow property. It is isotropic. It is higher near the wall than near the center in pipe flow. So all three options are right basically, because it is flow property, and also it is isotropic because eddy viscosity, and it is higher near the walls than the center. So option D is the right answer, which is giving 1, 2 and 3 statements. So the units of turbulent kinetic energy of energy dissipation rate are given by which of the following: joules per meter cube, joules per second, second per meter square plus second cube, or joules per meter cube second. So basically, how do we calculate? We just put all the known quantities and then calculate, right? Is anyone there actually? Okay, fine. Turbulent kinetic energy is given by, oh my god, turbulent kinetic energy is given by kinetic average, like it is the root mean square of the kinetic energy, right, as we have discussed before. So what is, I mean, root mean square of the velocity fluctuations. So it is given by okay. Mean square of velocity fluctuations. So it is meter square by second. So when it is turbulent kinetic energy dissipation rate, dissipation rate is given by so thereby it is meter square per second cube. So answer to this is option C, where it is given root mean square, I mean turbulent kinetic energy is calculated by as the root mean square of velocity fluctuation. So if we take it, meter square per second square is the unit. So the turbulent kinetic energy dissipation rate is given by meter square per second square by second. So again it is meter square per second cube. So answer to this problem is option C, which is meter square per second cube. So these are all the problems for today's session. I know I rushed in few places, so I mean I did it so because there should be continuity which should not be lost because of the weather conditions. So since there is time, I'll take few questions. I'll take the questions now. And if any one of you have any doubt at any part of this problems, so please feel free to ask. Also, yeah. Uh, since it is done, I'll just have a quick recap of today's session, followed by the quick recap of the whole problem solving sessions conducted so far. Yeah, before that, we'll just take a 5 minutes break and then resume the session. So yeah, we'll just start it back. I'll just give a quick recap of the session, followed by closing today's session. So basically, which of those is a characteristic feature of turbulent flows? So we know that turbulent flows are associated with chaotic fluid motion, high diffusivity, and high frequency fluctuations. And time interval for averaging should be larger than the largest eddy time period. And mixing length is plankton mixing length is associated with the distance between the distance the fluid particles takes before it I mean travel before it dissolves with the surroundings. So it depends on the normal distance from wall. And when we are solving the uh, case of a steady developing turbulent flow between two infinitely wide parallel plates, so what we do is we have one kind of continuity equations, two momentum conservation equations, and two energy turbulence equations. So adding up to 5. If it is a 3 dimension as shown in this, we would be having one more, which is 6. So here is a problem to calculate the velocity inlet for the flow to have a minimum Reynolds number. So basically it is given by rho Vd by mu. Since it is a rectangular duct, we calculate the equivalent diameter, and by doing so we get the velocity to be 2.1 meter per second. And since this is about a Reynolds averaged Navier-Stokes equations, here we are solving the unsteady form of the Reynolds average Navier-Stokes equations because the flow is turbulent. And yeah, it is 3 dimensional problem, so it is 6. And at a location, like, it would be greater near the walls than near the center. At the center it will be increasing with the time, but when we are comparing with near the walls, it would be more turbulent, because the fluctuations will be more when coming in contact with the walls. And it is which of the following are likely to be turbulent? For circular pipe, it is critical Reynolds number is 2000. For flow over a sphere, it is critical Reynolds number is 2 lakh. Flow over a flat plate, it is 5 lakhs. So circular pipe is 2000 and more, so 50,000 comes in that range. So the answer is flow in a circular pipe with Reynolds number of 50,000 is turbulent. Now we go to sixth question. It is like characteristic features of the turbulent flows. It is 3 dimensional and highly fluctuating and highly diffusive. And turbulence closure problems arises because when we do the time average thing, the number of equations arises and the unknowns remains same. Like, so we go for the turbulence closure problem because we time average the governing equations. And what is true about Reynolds stresses is that they are stress like quantities but not stresses, and there are 6 independent components in Reynolds stresses. Basically, when we do the time averaging of the Navier-Stokes equations, from the advection term we get the Reynolds stresses. So what is eddy viscosity? It is a flow property and it is isotropic as well. It is higher near the walls than the center of the pipe. What is the unit of turbulent kinetic energy dissipation rate? So we calculate the turbulent kinetic energy as the root mean square of velocity fluctuations. So its kinetic energy dissipation rate is given by 1 by second of the unit from the turbulent kinetic energy equation. The unit from the turbulent kinetic energy equation is meter square per second square, and the turbulent kinetic energy dissipation rate is given by meter square per second cube. So we'll just calculate the values. Unit as meter square per second cube. So these are all the problems from today's session. So we'll just, I hope all the problems from today's session is clear. Now we'll just have a quick recap of what are all the things we saw from class 1 to this class. If before that, if any of you have any questions, please ask. So basically, like, what are all the things we saw in this CFD course is that in the first week it was about introduction course, where the importance of CFD and various things, basic need for CFD were discussed, and followed by the uh, flow through a rectangular domain, where we discretize the system using finite difference approach and solved that, so that we would be it was easier for us to understand how things are happening. In the next week, it was about a triangular domain. When we were dealing with the triangular domain, we also saw how to discretize the system using finite volume approach. So, in when we are dealing with complex geometries, it is not always possible to go with the finite difference approach, or so we saw the finite volume approach discretization, and also like how variables are dealt either in cell-centered or face-centered. Everything we saw in the first two lectures, followed by we solved in the domain and discretized the domain and studied the system. And also we saw the various discretization schemes like central difference scheme, forward difference scheme, and backward difference scheme. So along with that, we also saw the different orders of approximations when we are dealing with such systems. So, in followed by, we also saw about um, different orders of approximations and how to go about that. And also we saw like always like how higher orders are not always accurate enough to deal with systems. I mean, it would be complicated to go with very higher orders. So basically, we should optimize it somewhere between computational efficiency and the uh, accuracy in the system. We should make a compromise between those two. And then we saw about the governing equations. I mean, yeah, I left out that we saw the governing equations with the mass conservation equations, momentum conservation equations, and also the energy conservation equations. And also we saw about the species and the species equations. And after that, we moved on to mm, all the governing equations we saw, and mass flow, how it is used in the systems when there are reactions involved. Everything we saw. And after that, we saw domains of like the different partial differential equations, like how to classify them as elliptic, parabolic, and hyperbolic equations, and what are all the domains of dependence and influence, and how those equations like how the classification of equations helps us in formulating the boundary conditions, so on. And together we also have mixed equations, sorry, mixed, and then we saw about the boundary conditions, which is Dirichlet boundary conditions and the Newman boundary conditions. I hope everyone is remaining in this. Dirichlet boundary condition and the Newman boundary condition. And in Dirichlet boundary condition, we specify the values of the variables along the boundaries, whereas in the Newman boundary conditions we specify the values of the partial differential terms, like flux values and all we specify in the Newman boundary conditions. And another one we have is the mixed boundary conditions, where we have both Newman and the Dirichlet in the system. Another is the Robin boundary conditions. This we saw as a problem in one of the sessions, where in Robin boundary condition we have the Dirichlet and the boundary conditions in a specified ratio, that is known as Robin boundary conditions. And after that we saw how to solve the Navier-Stokes equations in a system. Like we before that we also saw the various stencils for different equations and how to solve them. And after that it was about the need for analysis, like we saw the consistency, stability and convergence associated with the solving of the problems, with specific association to Lax theorem, like with importance was given to Lax theorem, which stated that for a well-posed linear initial value problems with a consistent discretization and stability is necessary and sufficient for convergence. That is, when the linear initial value problem is a well-posed one with consistent discretization schemes and the stability, like stability and consistency is sufficient for convergence. That is, if stability criteria and consistent criteria are satisfied, then we can assure that convergence is guaranteed. What is consistency is that if the solution of the discretized equation and the partial differential equation are same, then we say it is consistent. Stability is that exact solution of the discretized equation should match with the computed solution, then we say it as stability, or stability is achieved. Convergence is that the computed solution should match with the exact equation solution of the partial differential equations. So after that it was about need for the consistency, convergence and accuracy and stability, followed by the accuracy and how boundedness, consistency, all these concepts were studied. And also like stability criteria like von Neumann's analysis and how it is framed and all we saw. And the Courant number and was studied, like Courant Friedrich Levy condition for analyzing the stability was studied. And different schemes, how it behaves as conditionally stable or conditionally unstable or unconditionally stable, everything was studied in those systems. So followed by we saw the solution to the Navier-Stokes equations. In Navier-Stokes equation, how to solve them if it is compressible flows or if it is incompressible flows. For compressible flows we had a few techniques like McCormack scheme and beam warming scheme. And if it is an incompressible method, we had four different things. Like first one was artificial compressibility, where we put together additional terms to make it or similar to the compressible equations. And next approach is the stream function vorticity approach, which eliminates the P and transforms in the equations into stream function and the vorticity variables. And two other options are pressure correction method and the pressure equation method. Pressure correction method is a popular method for the incompressible flows, and it is mainly used in chemical engineering and hardcore engineering problems and all deals with the pressure correction equations. And another is the pressure equation method. In pressure equation method, we just calculate the velocity keep it as known and calculate pressure, and then calculate the continuity equation, and then calculate the momentum equation and calculate again the velocity and put it back in the continuity equations, and we see the mismatch and the loop continues. And also we saw about the staggered grid method, because checkerboard method there are oscillations. Checkerboard oscillations are pressure present in the system. So in such cases, it would not be possible to study the system with any fluctuations. Therefore, we go for the staggered grid approach, where pressure is studied at the phases and velocity and pressure is studied at the corner points, whereas velocity variables are studied at the face-centered ones. So with this, we were able to calculate the values to avoid the checkerboard oscillations. And after that, it was about the convergence analysis. Basic numerical techniques, like basic numerical methods to solve these equations were studied, and their convergence criteria were also discussed. So techniques like Gauss elimination, Gauss serial, Jacobi method, everything was discussed, and also with successive over relaxation, alternating direction implicit, and strong implicit procedure, and incomplete LU method, multigrid method, everything was discussed in further modules, with how these systems are explicit or implicit. In explicit, it is going in the step-by-step manner, whereas in implicit, we get the solution directly. Therefore, for steady state problems, implicit is effective. In the transient zone, these would not give the proper solutions. And also we saw about the multigrid method, where we have a series of grid sizes and solve the equations. Like we go with the finest grid and get the error, and put it in the next coarser grid and get the error, and put it in the next coarsest grid and get the error, and this loop continues. From the final coarsest grid, we get the error and put it back in the finest grid and get the solution. This reduces the error. So we also saw the different errors, and this method is highly effective in faster error reductions. And also we saw about the various convergence, how the convergence varies for different methods. And in the last class, it was about meshing with structured grid and unstructured grids. We also saw about body fitted grids, and also like unstructured grids. And like in unstructured grids, how to generate grid. Like grid generation is in 3 steps. We fix the boundary nodes and fix the interior nodes, and then do the triangulation. And the various methods of triangulation for unstructured grids, like advancing front method, Delaunay triangulation, everything was discussed. So how, like the difference between the structured and unstructured grids, and advantages and disadvantages associated with them was discussed in the last lecture. Last problem solving session, we also solved the problems associated with them. And in today, this week, the module was about time and length scale of turbulence and also the various turbulence models and how to characterize the turbulence. And if turbulence is present, what do we do to solve when we are solving the Navier-Stokes equations, and what kind of averaging we do, and Reynolds averaging and time averaged Reynolds equations, and the Prandtl mixing length model. uh, all these things were discussed even in the last class, I mean even this week's lecture, and so the problems associated with them are discussed in today's class. So that's all for the whole session. If there is any feedback from you people for this week's session or like whole session, please let me know so that I can improve in the further sessions. And I thank every one of you for attending these sessions and asking questions, so that it was helpful. And if at any point of time you felt any discrepancy in any of these uh, problems, please let me know. And these lectures are all available in YouTube also, given in the course website page itself, given as a link there, so you can access it anytime. And also I thank every one of you for attending the problems solving sessions, and all the very best for your future things. If if you watching it for understanding or for any purpose, I wish you all the best in your future. And also similar way for those appearing exams in this week, I wish you all the very best, and you will do well. Please like let yourself be calmed, and you know everything, like you people know everything. This is a general advice for any of the exam that you people are appearing for. uh, you have been preparing from the start of the semester to till this date, so you know everything. Just take a moment to relax. If you are thinking anything is hard, and feel relaxed, you would be doing very well. And like small advice from my side is, don't take anything at the last moment. uh, in terms of practice, do it from the start, it would be very helpful. And also, if it is a MCQ question, think well before answering. So that's all from my side. And if there is anything else you want to know regarding the course or any previous lectures are also fine, I can help you. We have nearly 25 minutes left, so you can ask any questions, so we can wrap up the session. So I think there is no questions from you guys, or I hope everyone is there. So then, if that is the case, we can just wrap up today's session. Okay, 20 more minutes are there actually, so we can just have a. mm, okay, like if you are like uh, doing this course in the BTech level for additional knowledge, then it is always worth it. Learn CFD with interest. It would definitely be helpful because all the modeling works of the systems at higher scales needs CFD, right? Because we cannot go about doing experimental stuff at larger scales, and therefore we need CFD. And also, like, if you have understood the concepts in the classes by professor, just start practicing by doing simple coding so that you can have a visualization. Any language would be fine. Just start doing the coding part, and by then you would be feeling very great associating with because you can imagine things while you are reading. When you start doing coding, you would be able to visualize it using systems, right? So that it would be very helpful. That is the advice from my side. But this course, and this is a very small portion of CFD, and I really think it would have helped you at some point. And so yeah, that's it. And I thank everyone for attending the session, and I thank the professor for giving me the opportunity to be the TA for this course. So that's it, guys. We have we have reached the end of the session, and yeah, I hope it was the problem solving session has helped you in some way. If not, I'll improve in the next term. Mm, please feel free to suggest your comments or anything. And all the very best for your future. And for those who are appearing in the exams in the coming week, I really wish you all the very best. And so that's it, right? Mm, we can stop presenting. I'll just wait 5 more minutes in case if anyone is joining or if anyone has any few doubts. After that, I'll close the session. Actually, and the problems are solved for today's session. So, do you have any doubts? Like, if in specific, I can answer now because I just completed everything. I mean, these are problems from week 12. Both the practice problems and the assignment problems are solved in today's session. So, in specific, if you have any doubts, you can ask me because you just joined now, right? Um, okay, guys, thank you for attending this and also like supporting me throughout the course by attending the sessions. I'll close the session now. Thank you.